Welcome to the third video for IB Astrophysics. In the last one we learned about the basics of stars, where they get their energy, what kinds of forces need to balance out to make them stable, that sort of thing. Today we're going to look at the basics of stellar observation. In other words, what can we learn about a star by looking at it? And it turns out that if you're quite clever, you can determine an awful lot of things just from looking at a star. First off, there's a number called luminosity, which is the total energy emitted by the star per second. Since it's energy per second, it's measured in watts, and it's usually a very big number. For instance, the sun's luminosity is 3.839 times 10 to the 26 watts, and it's a small to medium-sized star. So some stars can have a luminosity as much as 100,000 times that much. There's also a term called apparent brightness, which is defined to be the energy received per unit area, measured in watts per square meter. And you might remember we talked about this in the greenhouse effect section, where we called apparent brightness intensity. Essentially, it's how bright it looks, and it's measured in watts per meter squared. If you're asked to define it on a test, you must say energy received per unit area. And in this equation, B equals L over 4 pi d squared. D is the distance that you are from the star. So here's a quick exercise. A star has a brightness of 1.8 times 10 to the minus 8 watts per meter squared and is known to be 7 light years away from Earth. The question is, what is the luminosity? So first off, 7 light years is equal to 6.622 times 10 to the 16 meters. So we rearrange this equation, solve for L, 4 pi d squared b, plug that number in for d, and b is this value here. And we find that this star has a luminosity of 9.92 times 10 to the 26 watts, which is about 2.5 times as luminous as the sun. Quick notation bit, if you put a subscript that looks like a circle with a dot in it after something, that indicates the sun. So solar luminosity is L with that. Solar radius, same thing. So if you see the symbol, that means as applied, it means it's the sun. There's a bit more review from topic 8, Blackbody radiation, which is a particular pattern of radiation that looks like this. We have wavelength on the horizontal axis, and the intensity on the vertical axis. And you notice that it has 0 intensity at 0 wavelength. As the wavelength increases, the intensity increases too until it gets to a peak, and then it drops off at long wavelengths as well. And blackbody spectrums look pretty much alike, but as the temperature increases, two things happen. First off, the total intensity, the height of the graph, gets much, much larger at high temperatures. And the other thing is the location of the peak, which relates to what color it appears to be, shifts. For instance, at 2000 kelvins temperature, the peak is right here at a wavelength of about 1 micron. At 3000 kelvins, the temperature has shifted back a bit. By the time we get to 4000 kelvins, the peak is in the visible spectrum. And at 5,000 kelvins, the peak is green or yellow. So generally, the closer to the violet end of the spectrum something looks, the hotter it is. Also, since stars are nearly perfect blackbodies, we can use this equation for their luminosity. L is equal to sigma, which is a Stefan-Boltzmann constant, has this value, times A, the surface area. Since stars are normally spherical, A equals 4 pi r squared, surface area of a sphere, and T is the temperature in kelvins. That's important. It needs to be the absolute temperature, so we have to measure it in kelvins. So now how do we use that for stars? Well, the Wien displacement law also applies. This tells us how the peak wavelength moves. Lambda max is the peak wavelength, and that is something that is quite, well, I won't say easy, but quite straightforward to observe from a star. And it equals 2.9 times 10 to the negative 3 Kelvin meters, that's not kilometers, it's Kelvin meters, times, or divided by the temperature. Again, temperature has to be in Kelvin. And typically we'll use the color of the star, or more accurately its spectrum, and we'll find the temperature that way, and then if we can use the luminosity to find the radius. So for instance, a star called Antares has a peak wavelength of about 840 nanometers and a luminosity 57,000 times that of the Sun. We want to find its radius. So in order for this to, in order to find the radius, we need to find the temperature first. And so the first thing we do is we find we use the Wien displacement law to get that. T equals 2.9 times 10 to the minus 3 Kelvin meters divided by the wavelength, which is 8.4 times 10 to the minus 7 meters. And we end up with a surface temperature of 3450 kelvins. So it's significantly cooler than the Sun. The Sun's surface temperature is a bit over 5,000 kelvins. And that kind of makes sense because this peak wavelength here is well into the infrared, and the star Antares would appear red or orange where the Sun appears yellow. Now we know the luminosity. It's 57,000 times that of the Sun. Which is equal to 2.19 times 10 to the 31 watts. And we're trying to find the radius. So we're going to use the Stefan-Boltzmann law. L equals sigma times the area, which is 4 pi r squared, times t to the fourth. R equals L over sigma times 4 pi t to the fourth, all under a square root. And you put your numbers in. And you end up with the idea that Antares has a radius of 4.65 times 10 to the 11 meters. Now, that's a big number, but the question is, how big is it? Well, it's approximately equal to 3 astronomical units. So if Antares were to suddenly replace the Sun, Mercury, Venus, Earth, and Mars would all be inside Antares. That's how big it is. And so would part of the asteroid belt. So Antares is really big. It's what we call a red giant. We'll learn about those a bit later. What you need to know from today, you need to know the definitions of luminosity and brightness. You also need to be able to describe a blackbody spectrum, and use the Stefan-Boltzmann law and the Wien displacement law.